Good afternoon. My name is Dr. Scott Gerard, and I would like to talk today about multi-sensor fusion. So, a number of years ago, my colleague Suzanne and I went to an assisted living facility out in Oregon where we met the elderly occupants of 5 separate apartments, and we installed a collection of sensors there. And then we started collecting data from those sensors. Now, one of the apartments was occupied by a single elderly man, and when Sam, one of our other colleagues, got a hold of the data, he was looking at it and he said, "Wait a minute, I thought you said this was a single guy here, but there's 2 people moving around in this apartment." And that's when Suzanne and I looked at each other, smiled, and said, "Sam, the guy's got a dog. You're seeing a dog in the data." So our collection of sensors were not able to disambiguate people from animals. And now a camera could have done that easily, but because of our application, we did not use cameras because we thought they just posed too much of a privacy issue, monitoring, using cameras to monitor people's homes all the time. So the point of this story is that individual sensors certainly do provide valuable information, but a lot of ambiguity still remains when you're interpreting the data from that just one sensor. Aggregating and fusing data from multiple sensors gives you a much clearer and holistic view of what's going on because it dramatically reduces the ambiguity in the data that you've got. Now, you can't always reduce all ambiguity, but by combining data from multiple sensors, the AI that we use was able to convert these very low-level sensor readings into pretty high-level human behaviors. So that's what I want to talk about today to see if we can figure out some ways to use multi-sensor fusion to do this. So what is multi-sensor fusion? Well, there's kind of 2 flavors of it, but it's where you're taking data from multiple sensors to produce some kind of a unified picture. And one of the flavors is unimodal sensor fusion. And this is where you have a lot of sensors, but they're all of the same type. The other type is multimodal fusion, where you've got multiple sensors from multiple different types of sensors. And that gives you a different view on what's going on in your environment that you're monitoring. I think multi-sensor fusion isn't used as much as I would expect it to be used, but it seems to be widely applicable to fields like surveillance, autonomous vehicles, and robotics. So there's a lot of potential for multi-sensor fusion in the industry here. So why do you want to do it? Well, more sensors, more measurements give you improved accuracy and improved precision. That's one really good reason. You don't have to rely on one sensor giving you the complete story. You've got multiple that you can compare against each other. It also is going to give you better redundancy and reliability. So fusing data from multiple sensors compensates if one of the sensors isn't calibrated right or starts going wacky, or if it actually fails altogether and doesn't report any information at all. And the last one is, this may be a little non-obvious, but a single sensor may respond to multiple environmental parameters. So yeah, you get the sensor reading, but you don't know exactly what it corresponds to. And an example would be if you've got images of plants, right? That image is affected by both the lighting, by the growth stage of the plant, how much chlorophyll is in the plant, what kind of soil nutrients are in the soil, moisture, disease, and pests. There's a lot of things going on. And so a single sensor can be respond to a number of different environmental parameters, but by using multiple parameters, you can begin to remove that ambiguity and get much better discrimination on the data that you're looking at. There's 3 kind of main tasks that you're probably going to need to think about when you're doing multi-sensor fusion. The first one is, obviously you have to identify the object. If we're talking cameras, you need to be able to identify, there's a person here, there's a vehicle here, whatever target you're trying to track. Association is a little more complicated idea, which is if you've got multiple cameras, is person one in camera one the same as person three in camera two? You have to make sure that you're collecting data on a single object from these multiple sensors, and it may need to take some association to figure out which of the things that this sensor is seeing correspond to what the other sensors are seeing. You've also got to do some kind of registration. If you've got, and move everything down to a common coordinate system. If you've got a lot of different sensors and they're in different positions and they've got different orientations and they've got maybe different scales, how do you combine all that data? Well, you want to go to a common coordinate system. And a good way to think about this is a camera works in polar coordinate systems, right? It's from one point you're seeing out over a range of things. So it's either polar or perhaps spherical coordinate system. But if you've got multiple of these cameras, you're going to want to map them to some kind of a rectangular coordinate system. And so that's registration. You're going to register everything into one coordinate system. That's for the space component. For the time components, you're also going to want to, you may need to do some work to coordinate and register the time timestamps of the signals. So if you've got one sensor that's reporting measurements very frequently and other sensors are reporting them less frequently, you're going to have to figure out how you want to combine those sensor readings from different timestamps. And then the last thing is, it's not just a point measurement that you're getting from these sensors. Often the case is you have uncertainties associated with each one of those measurements. And some measurements have small uncertainties and some of them have very large uncertainties. So you need to be able to combine and fuse the uncertainties themselves. One way to do that is with an algorithm called covariant intersection. So now what I'd like to do is just, step back from the theory here a little bit and kind of give you some use cases that maybe help understand what's going on here. So in this particular case, let's assume we've got two cameras, one in the upper left-hand corner and one in the upper right-hand corner. And we're trying to figure out, and we're trying to track something through this space, whether it's a person or a vehicle or an animal or whatever. What are the uncertainties for the angle from the camera? I'm showing in this picture here 3 degrees of uncertainty, which gives it that kind of gray width there. But in a real camera, you've got uncertainties that are probably far less than even 1 degree. So cameras have wonderful certainties on the camera angle, but they don't have a depth perception. So what's the uncertainty on the radius in the polar coordinate system? Well, it's whatever the range of the camera is. It's completely unknown. But if you've got at least 2 cameras, you can do some coordination here and you can fuse them together. Most people will say, well, this looks like triangulation, and that's a very simple form of multi-sensor fusion. The processes that we're going to use here, particularly for the tracking case, there's a thing called the Kalman filter. It was invented in 1947. It assumes that you've got linear processes all the way through and Gaussian noise. Works really well if that's the problem that you're working with. The extension for that is if the processes are sort of linear, you can do kind of a Taylor series expansion around this and get to a semi-linear process, and that's what the extended Kalman filter does. But if the nonlinearities get even worse, you're probably going to have to move to an unscented filter, but they still have Gaussian uncertainties, and so that might push you all the way to a particle filtering where you could handle much more, you can handle generalized uncertainties as well. But so we're trying to track something through this space. We're going to use multiple sensors to do it. And the goal is to return an XY coordinate of where the target is over time. So this is one example of using unimodal multi-sensor fusion to figure out what's going on. Another interesting case is from precision agriculture. So let's assume that we have data of, multimodal data from the soil. We can get the moisture in the soil, the pH, electrical conductivity has some interesting properties. Maybe you've got hyperspectral or The next interesting case is precision agriculture. This is a multimodal data fusion case. We've got soil, and we may have moisture and pH and electrical conductivity from the soil. If we have hyperspectral or multispectral images of it, so these are pictures of the plant in multiple different wavelengths, that's definitely a different modality from the soil moisture. You have weather information, temperature, pressure, humidity, and even forecast. That's not a classic sensor, of course, but that might provide some really interesting information to this use case. And the problem here is that what we're trying to do is some object identification. So we're trying to identify what things are plants, what things are weeds, what things are pests. And we might use fuzzy logic, random logic, neural networks. There's a bunch of different things that you could probably try to use here on this. But the goal is one of two things. We're trying to figure out how healthy these plants are. And if they're not healthy, do they need more water? Do they need more fertilizer or more pesticides? We only want to apply those to the plants that need them and not apply them to the plants that don't. It's just saving resources, and it's also making it a much more sustainable agricultural system. But again, it's multimodal sensor fusion. This is a case that I worked on a number of years ago. I had an elderly couple in their bedroom at night, and we measured the CO2 levels in the bedroom at over 1,400 parts per million. Now, that's not dangerous, but anything over 1,000 parts per million is not good. And so they weren't really sleeping well because the CO2 levels had gotten way too high. So we were doing some sensor collection there. We were looking at the atmospherics, temperature, pressure, humidity, CO2, maybe some volatile gases. We also had these sleep sensors that went inside or in between the mattress, or in between the mattress and the box springs, that would tell us what the occupants' REM stages were of sleep and their heart and their respiration rates. Clearly a different kind of modality here. And we also could have put in some weather forecasting as well. What we did is we used some Bayesian networks, would have liked to have used some neural networks. The output in this case was one of two things. We were either going to make recommendations to the occupants saying, well, you know, you're not sleeping well, so you need to open or close the bedroom doors. Maybe there's some windows you want to open or close. And if we'd gotten really clever, we would have used, actually been able to hook into the HVAC system and maybe turn the fans on and off when appropriate. We didn't get this to work very well because we had one of the problems I'm going to talk about in a minute, which is very small training data sets. I also want to talk about knowledge graphs. We certainly want to have sensors in our system, but we have a lot of knowledge about what's going on in the environment or about the sensor systems itself, and those can often be encoded into a knowledge graph. And can we then take that knowledge graph data and make it a sensor as well? And the answer, I believe, is yes. I'm showing here 3 AI algorithms, AI 1, 2, and 3. The first one is you're taking data from the sensor system that you actually measure, the real sensors, and you're using that to find and inject and find a starting place in the knowledge graph of where you want to begin doing some work. AI2 then comes along and says, well, now that I've got a starting point from AI1, I'm going to follow some edges, get to some other nodes in its neighborhood, and I'm going to be able to expand out to collect more information. This is really exploiting the benefits of the knowledge graph, where things that are related are connected by edges. And then the output of those two then becomes another sensor reading that can go into AI3, which is where you're doing predominantly the AI or the multi-sensor fusion. Now, I've said that AI1 and AI2 are AI algorithms. They could be, but they could also maybe be very simple things as well. In particular, AI2 might just be a graph query operation. But in some cases, like AI1, you might do some embeddings to try to branch into the graph. But this is a way to think about how to extract information from a knowledge graph and incorporate it into this multi-sensor fusion. I talked a minute ago that one of the problems that you have when you're doing this multi-sensor fusion is that you don't have terabytes of data to use. I mean, ChatGPT has these huge data sets that they're getting off the web, but the systems that we're talking about in this case are IoT based systems, and we just don't have that kind of data typically for most of these systems. So we have much smaller training data sets to work with. And furthermore, in many cases, we're only looking for the anomalies in those cases. So most of the data is going along very well. It's normal, nothing to be concerned about, but we're looking for those anomalies. And the anomalies are rare compared to the normal data. We've got a small normal data set, so we have a very small sample of anomalies too. So this is one of the problems that you may need to deal with in this case. So what do you do about that? Well, the first thing to do is you probably want to start with simpler models. You don't want neural networks with thousands and millions of parameters because you don't have enough data to train them. But if you pick some very simple models, they require very much fewer parameters to work with to learn, and so that's a place to start. And interestingly, what you might want to do is start with the simple models, but continue to collect data so that you can build up your training data set. So in the future, you can come back and build a more sophisticated model because you now have more data. That's one approach to dealing with small training data sets. Another one is data augmentation. So this is where you look at your data and you perturb the data that you get to create additional training examples. So let's just take the idea of a sensor being an image. You can take a picture of a cat and translate it, some number of pixels to the left, some number of pixels to the right. There's still pictures of cats. They're still good training examples. Maybe you can rotate the image a little bit. Maybe that's a valid thing to do in your application. That's another way to get additional data set, additional training examples. And of course, you may play with the color, like take color and just go to black and white and get additional samples there. And, mix and match them and go with multiple perturbations. Again, you have to look at the sensors that you're working with and figure out what kind of perturbations make sense for that sensor. But that's another way to, multiply the size of your data set by some small factor, 3x, 5x, maybe 10x kind of thing. The third example is synthetic data generation. If you understand the domain model really well, you could write an application that executes that domain model and generates synthetic data right out of the model. That's one way to do it. Another way is you take the training data set that you have. If you have enough to train an autoencoder, then once you have the autoencoder, then it can generate more training samples for you as well that follow the same distributions that you learned. And that's another way to approach the problem. The thing you need to watch out here is that if your domain model, your autoencoders didn't really learn the right thing or all of the right attributes, you may be introducing bias into your training data set. And that's something to kind of worry about. So I hope this was interesting to you. I think data fusion is an evolving field. It's at the intersection of all this cool IoT technology and AI technology, and there's a lot of cool math going on behind it. It's multifaceted, so there's not just one scenario that will apply to everybody. Every different scenario requires different methods and different ways to look at it, so it's a challenging and interesting area. But just stay informed and keep up with the theories and the technologies that are going along. And if this is of interest to you, I would love to have a chat with you and continue the discussion. So thank you for your time, and I hope to hear from you.